In this video, we are going to talk about exact differential equations. We'll start with the definition, which is if you have an equation, a differential equation, mxy plus nxy times y prime equals 0, it's considered an exact differential equation if this part here can be expressed as an exact derivative of a specific function. And that specific function we're going to call psi, and that psi, again, the derivative of psi will give us our m plus n y prime. We will look at this theorem, which will tell us when an equation m plus n y prime is exact, and it is exact when partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. And then we'll be able to find a psi. And the proof of this theorem actually is constructive and will help us find psi. We'll do some examples. And then last, for equations that are not exact, we are going to look into finding an integrating factor that will then allow us to solve the equation. Backing up, we'll look at the formal definition of an exact differential equation. So we have the form of the differential equation, mxy plus nxy prime equals 0. And we'll call it exact if it can be expressed as an exact derivative of a function. By the way, you might recall this form. We talked about that when we talked about separable equations. And for separable equations, we assumed that m was only a function of x and n was only a function of y. We have this theorem for exact differential equations, so let m with respect to y, and n with respect to x, where the subscripts denote the partial derivatives, be continuous in the rectangular region x between a and b and y between c and d. Then the equation mxy plus nxy times y prime is equal to 0 is an exact differential equation in R if and only if partial derivative of m with respect to y is equal to the partial derivative of n with respect to x at each point in R. That is to be an exact DE, that means there's a function psi that satisfies the partial derivative of psi with respect to x is equal to mxy, and the partial derivative of psi with respect to y is equal to nxy, if and only if m and n satisfy the condition of the theorem. What we will do is an example first, just to get a general feel for what's going on. Then we're going to use our example to help us solve the general solution, the general example, which is mxy plus nxy times y prime is equal to 0. We'll use this then to do a proof, and the proof will be constructive. It'll tell us how to find psi. And then once we have kind of instructions on how to find psi, we'll do some more examples. Our first example is to solve 2x plus y squared plus 2xy times y prime is equal to 0. And I rewrote this. I often like to see my y's in terms of x, just to remind myself that y is a function of x. And just to compare this equation to differential equations we've learned how to solve in the past, first, this y squared means it is not linear. This is not a linear differential equation. Second, this x times y makes it not separable. Remember, to be separable, we assumed m is only dependent on x and n is only dependent on y. Here we have y prime, so here n is dependent on x and y, so it is not separable. What I have is once I find my psi, when I take my psi with respect to x, and then I add it to d psi with respect to y, and since y is a function of x, I have to multiply by the chain rule, I have to multiply by dy dx is equal to 0. So what I notice, and this won't be such a magical, like how did you get this later, because we will define a way of how to find this function here, psi. But what I noticed is if I let psi be equal to x squared plus xy squared and then take the derivative with respect to x, so this is going to be 2x, and here with respect to x, remember y is a function of x, so I'm by the product rule, I'm going to have x times the derivative of y squared, which is 2y times dy dx. Remember, it's the product rule and as well as the chain rule. And then I'm going to have the derivative of x, which is 1 times y squared. And if I look at this, this is 2x, and then I have my y squared of x, and then I have my 2x here times y of x dy dx. So this here is exactly this equation here, which means my psi is equal to x squared plus y squared. So when I integrate both sides of the equation, I get psi is equal to, and when I integrate 0 dx, I just get c. So this is my implicit solution. Did you see how I pulled this out of a hat without explaining how I got it? Don't you hate when teachers do that? So I am going to beg your forgiveness and tell you that I will explain later in this video how to find this value. So that was our first example. So now we're going to look at solving the general equation here, the mxy plus nxy, y prime equals 0. To look for a general solution, I started here by putting our last example up here for reference. But the idea is if we're looking at the equation, mxy plus nxy times y prime equals 0, we're going to start by supposing we can find a psi of xy such that the partial of psi with respect to x is equal to mxy, and the partial of psi with respect to y is equal to nxy. So I haven't shown you that this is definitely possible, and I haven't told you how we would do this, but for now I'm just going to say, let's assume that we can find this psi. And furthermore, we can have an initial condition, so psi of xy equals c will define a particular solution implicitly. So then our equation, our original differential equation, then becomes d psi dx plus d psi dy dx, right? Just plugging in for m and n. And this here, by the chain rule, because d dx of psi will give us d psi dx plus d psi dy, and by the chain rule, dy dx. So this is actually just equal to d dx of psi. In our previous example, our psi was this x squared plus x y squared, because d dx of psi was equal to our integrand, and so when we integrated, we got psi. So that is what we're hoping for here. So again, we're going to assume we can find psi that fits this description here, and we'll see that then our psi, d dx of psi, will equal to our original, this left-hand side of our original differential equation. We are going to use that idea in our proof, which will be constructive and give us a method for finding psi. From our previous work then, we said that if we can find a psi such that d psi dx is equal to mxy and d psi dy is equal to nxy, then our original differential equation becomes d dx psi of x v of x equals c. In other words, our original equation, this left-hand side, mxy plus nxy y prime, will be the derivative of psi. This is what this is telling us. So in other words, our equation is exact. So in this proof, when we talk about exact, we are going to use this condition here, that we can find a psi that satisfies these conditions. And I've rewritten this here, that to be exact, we're going to use the fact that that means there's a psi such that the derivative of psi with respect to x is equal to mxy plus nxy y prime. Now there are two parts to this theorem because of the if and only if, which was right here. So the forward direction, so the equation mxy plus nxy y prime equals 0 is exact. So again, this is our hypothesis. Then we have this condition, my is equal to nx. So here it is. This is our the forward direction, first part of our proof. The second part is the opposite direction that uses the my equals nx as the hypothesis, and then the opposite way, that will imply that our equation m plus ny prime equals 0 is exact. So there are two parts of this proof. We are going to start with the forward direction. So we're going to assume that the equation is exact. So there is a psi such that psi of x is equal to m and psi of y is equal to n. And then, kind of repeating some of the calculations we did on the previous slide, d psi dx is equal to d psi dx plus d psi dy dy dx, and this part comes from the chain rule, so this is equal to our m plus n y prime. We're going to look at my, that is m partial derivative with respect to y. So my is equal to d dy of m of x, which is equal to d dy of psi of x, because psi is equal to m is equal to m. So this is psi partial derivative with respect to x, partial derivative with respect to y. And if you remember from vector calculus, it doesn't matter which order we take this derivative in, so that's equal to psi of yx. And if you don't remember this from vector calculus, which I guess for a lot of you was a long time ago, like last semester, we'll just go through it with a quick example, so I'm not going to prove it in general. But remember when we had a function like 2x squared y cubed, and we took the partial derivative with respect to x, treating y like a constant, that would give us our 4x y cubed, and partial with respect to y would give us our 6x squared y squared. And then when we took the derivative of this with respect to y now, that would give us our 12xy squared, and this derivative with respect to x now, that would give us our 12xy squared. So it didn't matter if we did the partial with respect to x and then y, that would equal to the same thing as doing the partial with respect to y and then x. So that's what this is here. Similarly, we can look at nx, which is the partial with respect to x of n, which is the partial with respect to x of psi of y, which is equal to psi yx. So these two now are equal, but since they're equal, that also means that my is equal to nx. So what we have shown is if our equation is exact, that means the partial with respect to y of m is going to equal to the partial with respect to x of n. And now we are going to prove the opposite direction, which is if we know my is equal to nx, then we know m plus n y prime equals 0 is exact. And we will do our constructive proof, which is kind of exciting. It will show us how to find the psi. No more pulling functions or having to guess at what the psi might be. You'll have an algorithm which will tell you how to do this. Our psi meets these conditions here. So psi of x is equal to mxy. So when we integrate both sides, we're going to get psi is equal to some function plus some function of y. Since we're integrating with respect to y, any function that's only dependent on y, when we take the derivative of psi, will go away to 0. So it's sort of like the way you add plus c. Now we can add a whole function of y, which goes to 0 when we integrate. So again, psi is equal to some function plus h. Now we want to choose h of y such that d psi dy is equal to n of xy. Remember, that was kind of our condition here. So what we have is d psi dy, here is our definition of psi, is equal to dq dy plus h prime of y. And again, this we want to equal to n of xy. So what that means is h prime of y is equal to n of xy minus dq dy. And again, this here will be a function only of y. And here are the instructions for how we are going to construct psi, right? We take psi, we set it equal to m, and then we integrate both sides, we get psi right here. Except it's not quite done because psi also has this h of y, but here we have the instructions on how to figure out h of y. And here you know how I said that this portion here, h prime of y, is only a function of y. Here's the proof, which I'm not going to go over, but it's here for your reference. And actually I should say, so we have our h of y here, but it's h prime of y, so we integrate to find h of y. Here is what we just talked about, kind of shrunk down, so that I can put the main two steps right here. This is how we find psi. And now that we have those two steps, we can do more examples. I have from our proof our method of constructing psi summarized in these two steps. Our next example then is to solve the equation 2x plus y squared plus 2xy y prime equals 0. And I start out again by rewriting and emphasizing the fact that y is a function of x. And then I separate out my m, those are all the things that are not multiplied by y prime, so it's 2x plus y squared, and then my n, and those are the things that are multiplied by y prime, so that's 2xy. So the partial derivative of m with respect to y is equal to 2y, and this is 0, so 0 plus 2y. Our partial derivative of n with respect to x is going to be 2y. Since they are equal, then that tells me that the equation is exact. Looking at my method here, I note that the integral of psi with respect to x, so I copy that down, is equal to the integral of mxy dx. I copy that down, and then I plug in my mxy in here. So I have the integral of 2x plus y squared dx. So what that gives me is when I integrate this, psi, derivative of psi with respect to x, then integrated with respect to x is just going to give me back my psi. And over here, with respect to x, I'm going to get my x squared and my x times y squared, plus some arbitrary function of y, right? So if h is just dependent on y, when we take the derivative, it will go to 0. So this is kind of like a constant because y is considered a constant. This here then, according to this method, this will be my q of xy. Compare where we are to this construction of psi. So we've taken the integral, so now we have psi of x is equal to q of xy plus some function of y. So here's my psi of xy, here's my q of xy plus some function h of y. The next step is to solve for h of y, which I've rewritten here, is equal to the integral of n of xy minus derivative of q with respect to y, and we're integrating with respect to the variable y. So my n of xy is written here is 2 of xy, and then the derivative with respect to y of q of xy, and q of xy is x squared plus y squared x. So here's my q of xy. So I have my 2xy minus derivative of this with respect to y. Well, this x squared goes to 0, and this term goes to 2xy. So I have my minus 2xy. And you see these two cancel out, and all I am left with is a constant c, which means then my psi is equal to x squared plus y squared x plus my constant c. Psi here is our implicit solution, but I'm going to just kind of plug it back into the equation just to make sure that we understand what it is that psi is. So when we integrated both sides of our differential equation, so I'll just start with the original equation here, integrating both sides. So I integrate 2x plus y squared plus 2xy y prime with respect to x, and I'll integrate this side of the equation 0 dx. And what we found here, this psi, was the antiderivative of this. So the antiderivative would be x squared plus y squared x. And in this case, I'm not going to put the c because I'll just use the c over here, which is equal to, and 0 dx is equal to c. So this is our implicit solution, which you can see we had already gotten as psi. But again, the whole idea of psi is that when we took the integral of both sides of the equation, we would end up with psi as our solution. The next example I have is solve y cosine x plus 2x e to the y plus sine x plus x squared e to the y minus 1, all of this part multiplied by dy dx, or y prime. Identifying my m function here and my n function here, so m is equal to y cosine x plus 2x e to the y, and if I take the derivative with respect to y, I get cosine x and then 2x e to the y. Our ny will be equal to the sine x plus x squared e to the y minus 1. Taking the derivative with respect to x, this would become cosine x, and this here would be 2x e to the y, and the minus 1 goes away. And in this case, you can see that my is equal to nx, and therefore this equation is exact. Using our method here of finding psi, I have the integral of psi with respect to x dx is equal to the integral of mxy dx. So I've written that here, and then I plugged in mxy, which is y cosine x, plus 2x e to the y dx. I integrated this, and I get y, with respect to x, so I get y sine of x plus x squared e to the y plus some function of y alone, because this function will go to 0 when you take the derivative. So far I have psi of xy is equal to y sine of x plus x squared e to the y plus h of y. And this part here is q of xy. So I've done this first part of the equation. Now I can solve for h of y. I'm not sure why I put number 3. This should be number 2. H of y is equal to the integral of n of xy minus dq dy, and we integrate with respect to y. So I'm going to first plug in my n of xy, which is written over here, sine of x plus x squared e to the y minus 1, and I'm going to subtract derivative of q with respect to y. So here I will get, remember x is a constant, so I have y times a constant, sine of x, and then I also have this with respect to y is just x squared e to the y. That's also a minus. And then this part, this whole thing, I have to integrate with respect to y. But you can see that this term will cancel with this sine of x, and this term will cancel with this x squared e to the y. So all I'm left with is this negative 1, which is just integrates to minus y plus c. So now my psi equation is y sine of x plus x squared e to the y minus y, and that all equals c. And this is my implicit solution. And I would recommend doing a quick check of my psi by taking the derivative with respect to x, and what you should get back is this equation here. I mentioned before that this form of the differential equation mxy plus nxy times y prime equals 0 should look familiar, because when we looked at separable equations, we looked at the special case where m was only dependent on x and n was only dependent on y. And this was an example we had from there, and I wanted to do this example in terms of the general differential equation. And of course this is going to be exact because it's the simplified form. But anyway, the example we had done from 2.2 separable equations was dy dx is equal to 4x minus x cubed over 4 plus y cubed, which I rewrote here. So looking at this, I multiplied this side so that I have 4 plus y cubed dy dx minus, and I moved this over, 4x minus x cubed equals 0, so that I have this mxy plus nxy times y prime equals 0 form. And actually, I swapped this around so my m could come first. Here's my n. So my partial derivative of m with respect to y, again, because m only depends on x, is 0, and my partial derivative of n with respect to x, and again, n is only dependent on y, so that's going to be equal to 0, so it's automatically exact. So the separable equations are indeed exact. And then just following the same method for finding psi. So I have the integral of psi is equal to the integral of m, so I plug in m, which is x cubed plus minus 4x dx. With respect to x, I get 1/4 x to the 4th minus 2x squared plus hy. And then following my procedure for finding hy, that's the integral of ny. Here is 4 plus y cubed minus derivative of q. Where is q? It's over here with respect to y. And because q now is only has variable x, that will be equal to 0. So the integral of 4 plus y to the 3rd will be 4y minus 1/4 y to the 4th. So our psi is equal to 1/4 x to the 4th minus 2x squared plus y to the 4th minus 1/4 x to the 4th, which is exactly what we got when we simply separated and then integrated both sides of the equation. One more example before we go on to our next topic. We'll solve 3xy plus y squared plus x squared plus xy, all of this times y prime equals 0. Our mxy is equal to 3xy plus y squared, so m with derivative of m with respect to y is going to be 3x plus 2y. Our nxy is x squared plus xy. So our derivative of n with respect to x is 2x plus y. So you can see, actually they're not equal. So since my is not equal to nx, the equation is not exact. Which brings us to our next topic, to attempt to find integrating factors for equations that are not exact. And this is analogous to the integrating factor here that we used for first order linear differential equations. We have mxy plus nxy, y prime equals 0, but this equation is not exact. We're going to multiply the entire equation by an integrating factor mu xy. And then we have that the equation is exact, this equation with the integrating factor is exact if and only if the partial of mu m with respect to y is equal to the partial of mu n with respect to x, a very similar condition that we had for exact equations. The partial with respect to y of mu m, since mu and m are both functions of y, we're going to use the product rule and will come in two parts, which I have underlined in blue. So first we'll have m times the partial of mu with respect to y, and then we're going to have mu times the partial of m with respect to y. So that's here. Similarly, when we look at mu n with respect to x, that will come in two parts, and that will be by the product rule, mu of x times n, which is right here, and then we'll have n of x times mu. So here's n of x times mu. And then since these two are equal, what we'll have is when we sum them all together, we'll get that equal to 0. And now that we've done all this work to get this equation, we have this comment that this equation here, we just figured out, is usually at least as hard to solve as the original equation. But it is the case that if we have an integrating factor that is only a function of x or y, not both, then sometimes we can solve this. And one other comment before I go on. If this equation has more than one solution, any solution can be used as the integrating factor. Okay, so our special case, mu is only a function of x, mu of x. Have the partial of mu with respect to x is d mu dx, and the partial of mu with respect to y then, since it's only a function of x, is equal to 0, which means our complicated equation here, m partial of mu with respect to y minus n partial of mu with respect to x plus my minus nx times mu is equal to 0 now gets simplified. This is 0 here, and what else is 0? I think that's it. So we have n du dx plus my minus n of x times mu. So that means is equal to 0. So that means our d mu dx is equal to my minus nx over n times mu. And I have our notes here. So we have our original equation that we said was not exact, so we multiply the entire equation by our integrating factor mu. And then we said the equation is exact if and only if mu m with respect to y is equal to mu n with respect to x, which gave us this complicated equation. And we said we're going to look at the case when mu is a function of x only. And then we have this relation. If that's the case, then d mu dx is equal to m partial with respect to y minus n partial with respect to x over n times mu. So we're going to do an example, find an integrating factor for 3xy plus y squared plus x squared plus xy times y prime equal 0. And this is the very same equation where we showed that the equation was not exact, and we used this equation to introduce integrating factors. So now we can solve it. I'm going to start by working at this top part of this formula. So m with respect to y minus n with respect to x. So here's my m with respect to y. I'll get 3x plus 2y minus nx. So over here, with respect to x, I get 2x plus y. I have this, and what I have left is x plus y. Now I need to put this over n. So I'm going to put my x plus y over n, which is x squared plus xy. Factoring this out, I'm left with 1 over x. So plugging into this formula, I have du d mu dx is equal to mu of x times 1 over x. Now this is a separable equation, so I can move my mu over and keep my x's on this side. So moving this over, I get 1 over mu of x d mu dx is equal to 1 over x. Integrating both sides of the equation with respect to x, here I get natural log of mu of x equals natural log of x plus c. Raise both sides to the e, and I get mu of x is equal to e to the c times x. So I can let c equal 0. Remember, when you have multiple solutions for mu, you can just choose any. So choose the easiest. Let c equal to 0, so mu of x is equal to x. We were asked to find the integrating factor for this equation, which we did. We found mu of x is equal to x. This did not ask us to solve the equation, but I'm going to go ahead and do that just to demonstrate. So multiplying the entire equation by my integrating factor, I'll get 3x squared y plus xy squared plus x cubed plus x squared y times y prime equals 0. Identifying mxy is equal to 3x squared y plus xy squared, I can take the partial with respect to y, and I'll get 3x squared plus 2xy. Similarly, my nxy is this portion in front of the y prime, which is x cubed plus x squared y. I can take the partial with respect to x, so that's 3x squared plus 2xy. And you can see my is equal to nx. So this is an exact equation. In other words, here the equation multiplied by the integrating factor is an exact equation. To continue to solve our differential equation then, I'm going to use our method here where we find psi as qxy plus hy, and then we find h of y. And for our reference, I rewrote those two steps up here. So starting with psi, I have the integral of psi xy dx is equal to the integral of mxy dx. So I'm going to plug in my mxy, which is 3x squared y, plus xy squared, integrate with respect to x, and I'll get I'll get x cubed y plus 1/2 x squared y squared plus some function of y, which goes away if we take the derivative with respect to x. For hy, I'm going to get the integral of nxy minus q with derivative of q with respect to y. All of this integrated with respect to y. So ny first, which is over here, x cubed plus x squared y minus the derivative of q, which is this portion of my psi, minus x, with respect to y, will give me x cubed, and then my y will give me x squared times y. And you can see the x cubes cancel out and the x squared y cancels out, so h is equal to 0, and our psi is equal to x cubed y plus 1/2 x squared y squared. So this is our implicit solution. Although we really were complete and had finished our problem once we found psi, I'm just going to back up once just to make sure we understand why psi is the solution, or why psi is the solution. This was our original, not our original, but our equation multiplied by our integrating factor here, the 3x squared y plus xy squared plus x cubed plus x squared y times y prime equals 0. So when we solve this equation, we integrate both sides with respect to x. And the thing about psi is the derivative of psi is equal to what's on the left-hand side. In other words, the antiderivative of the left-hand side is equal to psi, and the right-hand side gives us c. So this is the solution to our equation, to our differential equation. To review what we've done, we looked at exact differential equations, which meant our mxy plus nxyy prime equals 0. This equation was an exact derivative of a specific function, which we called psi. We had this theorem that said that a function would be exact, or this equation would be exact, if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. We did a proof which gave us this two-step process in constructing psi. And we did some examples. And then we also looked at what would happen if we had equations that were not exact. Can we multiply by an integrating factor to be able to solve the solution? And the answer is we could do that if mu was a function of only x. And then we have this equation for finding mu, and we did examples of that. So that's it for this video. Thank you for watching.